Hey guys, so I know it's been pretty hot lately outside, really hot, especially where I'm um, based. So I had decided I had to do something to chill, and don't try this at home. I guess you're all kind of seeing where I'm going with this. So I have here a small thermos flask. Let me just shut off the light so you can see more clearly. With liquid nitrogen. You can see it in there. Not really boiling because this vacuum flask is an excellent insulator. It's in this towel to catch any drips, but not really, and it's in here just for mechanical stability because the bottom of the flask is very rounded. So let me just add some more LN2 and let me just see what I'm doing here. I don't know if you can actually see the liquid pouring, but you can definitely see the fog. That's just the moisture in the air condensing when it hits the ultra cold, boiled off nitrogen. So this is just a regular dual wall vacuum insulated flask. It's very nice. It cost me a cool $3 at the flea market, and let's see what happens when I put this gag circuit in the liquid nitrogen. You can see it's boiling in there. So I'm just gonna dip the transistors in. I think it's also cooling the capacitors a bit. But you can see they kind of stopped completely. So at cryogenic temperatures, these transistors behave very weirdly. One of the LEDs is completely turned off now. Yeah, let's do another classic experiment involving liquid nitrogen. And let me just go here to the Keithley. I'm sorry I can't fit everything in the frame because it's just it's too much, like too much stuff to put in one frame. So I'm gonna look for my green LED and I'm gonna connect it up, and you can see what I'm doing, right? So it's just a regular green LED. It's lit up pretty dim right now. Let me just give it a few more milliamps, something you can see. You can see it's very green right now. And if I dip it in the liquid nitrogen, that's not the camera trickery, because you can see my hands are still the same color. The lead has turned yellow. Why is that? Well, due to the fact that this is a very cold substance. It's 77 Kelvin, give or take, so it's negative 190 something degrees. The semiconductor material, and you can see it's gone back to being green. The semiconductor material actually changes its parameters, its band gap and stuff like that, and it behaves very differently, and the green LED will turn into a yellow one. This is kind of the only LED color that really works well for showing this thing. Okay, let me just rearrange the camera a bit, and we'll dip the PT100 and measure the temperature of this thing, and we'll see just how cold it gets. And then I have some more measurements to show you. Be right back. Right, so I'm sorry about the terrible backlight. Jesus. But this is the best that I can do. I hope you can see the display for the Prema. And I'm gonna dip the PT100 in the liquid nitrogen, and you can see it boiling off, cooling it down. And look at the display. Negative 46, 55, 70. This is already colder than... oh, it's way past that. I was gonna say it's colder than dry ice by a very significant margin. So we're nearing the... right, so It's a bit too cold actually, because regular liquid nitrogen is around 195 degrees below zero. So it's either nonlinearity of the PT100 or something, but you can see it's insanely cold. Like really, really, really stupidly cold. And this is the rain where uh, materials don't really behave as they used to behave at room temperature. So what can we do with this? Well, first of all, one of the main uses for this thing that I know in science is cooling down detectors, like, for example, high purity germanium detectors for gamma spectroscopy need to be cooled to cryogenic temperatures to work, because otherwise they would just conduct far too much current at any voltage, and yeah, there's a whole lot of physics in there, and they wouldn't work. Basically, you would just burn them up immediately. So this is one of the main uses for liquid nitrogen in science that I know of. It's got a lot of various uses, I'm sure, but this is the first I've ever seen. And funnily enough, it's boiling right now, and it's boiling not that vigorously, because, as I said, the insulation for this flask I got is really good. You can pretty much comfortably set your hand on the outside for a while, and you won't stick your fingers immediately to it. It's pretty good. Okay, so what I'm gonna do is pause the video again, and I'm gonna show you the setup I have for measuring various things. I'll be right back. Right, so what I have here is the Keithley 237. I can can't see it fully, and it's right now it's actually acting as a current source, and it's sourcing 10 milliamps through this green LED I showed you, and the VF of the LED at this current is around 2.1 volts. Let's see what happens when I dip it in liquid nitrogen. Can you see it going up? It's actually gone up to almost 9 volts VF at the same current. Yeah. And you can see it's yellow now. I don't know if you can see it. Yeah, you can still see it's yellow. And it's turning back to green as we speak. So this is basically what I'm gonna do, and I'm not gonna show you the entire measurement for all the things I'm gonna characterize, but this is basically what I'm gonna do. I'm gonna do a VF, practically an IV diagram for several pieces of silicon that I have lying around, and then I'm gonna plot them on the screen, and I'm gonna show you what each and every one of them is and what it means. And then we're going to try and do a characteristic curve, like a family of curves for a transistor, using the 4145 over here. You can see it's warming up, and we're going to see how the gain of the transistor changes with extreme temperatures. I'm gonna have to figure out first a way to actually get the transistor cold in the fixture. I think I'm just gonna use some wires and some pins or something like that. Then I'm gonna move the small dewar up here, and I'm gonna rearrange the camera a bit, and we'll see. Okay, so I'll be right back. I think I'm gonna try and do the transistor thing first, because I don't want to run out of liquid nitrogen, because I've already done all the diodes that I plan to do. So let me figure that out, and I'll be right back. Alright, so I've filled this cup to the brim. The transistor is around here, and I'm gonna move it slightly closer in and dip it inside. And while I'm holding it like that, I'm gonna hit measure on the 4145. You won't be able to see, but I'm going to hit single. Right, so we got results. Finally, that was pretty difficult to do. So let me move you again, and we'll take a look at the screen and see what we can understand from that, because it's very, 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 very interesting. Yeah, I'll be right back. Just a second. Right, so what we have here is this is the characteristics of the transistor at room temperature, the dimmer lines. And this one right here is the characteristics of the transistor at, you know, as close to absolute zero I can get it. So 77 Kelvin basically. And what we can see is that at very low temperatures, the transistor seems to saturate a lot quicker. So the collector emitter voltage in saturation, which is this region here, is much smaller. I have no idea why that happens. It's probably because the gain of the transistor changes, but I'm not entirely sure. It might just be something to do with the collector emitter voltage just dropping very much when the transistor is very cold. What you can see is that I think I might be right. You can see that at lower base currents, the gain is considerably higher. So this is the smallest base current. I don't know what exactly I set it to, but this is lower and it's going 50 by in 15 microamp increments. So you can see that the lowest curve on the cold transistor is higher than the lowest curve on the warm transistor, but it evens out at some point. I don't know why. Yeah, so this is extremely interesting. Let me try another measurement, see where we're at now. And if I hit auto scale again, you know what? I think I might have just been confused by the fact that the recalled shape isn't scaled according to what it used to be. But look at this characteristic. It seems much flatter, so the saturation region seems much flatter than the warm transistor, and yeah, I don't know, it's very weird. Now it's warming up because I took it out of the thing, so it's very close to room temperature now again. It's very interesting. And let me dip it back in. So let's do some actual science here. So we have around 700 microamps of collector current at the top of the thing here. We're just gonna look at that one, and the slope is, I don't know, about 70 degrees from here, something like that. And let's remember 700 microamps, and it's looking like 70 degrees, I'm gonna call it. It's not very scientific. Anyway, so I'm gonna dip it again in liquid nitrogen, let it cool down, and we're gonna do another measurement. But I'm also gonna hit store on this one, and let me do the dippy thing. Oh, and you can also see the early effect manifesting itself. This line is obviously crooked and it's going up. So let's do another single measurement. Oh, and you can see now this is the current range stayed the same. So the gain of the transistor has massively fallen due to the lower electron mobility you'd associate with very cold temperatures. And you can see it's kind of erratic, so I'm going to do another measurement with a longer integration time, which is a mistake because it's never going to finish. Let's try it again. I think the transistor is not working as a transistor anymore at these voltages. Temperatures, sorry. So we're in the... Basically, I think we're almost in the noise floor of the instrument, because once I hit auto scale, it's going to completely go crazy. I wish I had a JFET to do this on, but I don't have any JFETs. Now let's hit auto scale again. Now let's see what happens. Oh yeah, so we're in nanoamps and 4145 is freaking out. Let me pause the video and I'll try and do a long integration time measurement and see what happens. I'll be right back. Right, so we have a result. Incredible. So I think the current here is not really correct. But anyway, what we can see is that this is the linear region, this is saturation. And remember we had around 700 microamps and the ramp, basically the saturation region went up at, I called it a 70-degree angle. Well, now it's almost vertical and it only goes to 186 microamps. So in this case, I think let's check what the values were for so the beta of the transistor is only around 18, and at room temperature it was, sorry, so at most it was 50 microamps, so it's only around what is 180 divided by 50 microamps? It's around 3.5, something like that. So 3.5, and that's 600 microamps. If you divide that by 50-ish, you get around 10. So this is a very low gain transistor as it is, but it gets even worse at very, very low currents. So yeah, and it took its sweet time, like it took over a couple of minutes to do all the points of measurement, but you can see that even at very, very low currents, it still did a reasonable job. Alright, so I'm going to open up some photos, basically some captures of the IV software that I used to characterize various diodes I had, both at room temperature and at cryogenic temperatures, and we can take a look at them and discuss them one by one. Okay, I'll be right back. By the way, look at what happens to a crocodile clip when you freeze it solid. It can barely crack it open now that it's warmed up a bit, but everything becomes very brittle when you put it in liquid nitrogen, especially plastics. Come on, how cool is that? Negative almost 200 degrees C and the tip of your fingers. It's frozen solid. Cool. Alright, so what we have here is the VF of an LED at room temperature. So you can see it's about 2.5, something like that, 2.2 volts. Sorry, not 2.5, 2.1, 2.2 volts. For 10 milliamps of current through the LED. If we go to the next photo, which is at 77 Kelvin, you can see that it does a very weird thing. First of all, it spikes to around 10 volts, which is crazy. I didn't expect it to go that high. And then the further the current increases, the lower the voltage gets. So it's almost like a negative resistance thing. So yeah, it's very interesting. Cryogenic temperatures are very weird. This is the LED that turned from green to yellow. Right, so this is a yellow LED. You can see the VF is slightly lower. It's around, I don't know, 2 volts or something like that, 1.9 volts, something like that. And when you put it in liquid nitrogen, it looks even weirder. So it spikes up to 8 volts again, and then it drops abruptly. Like, it's very weird. It looks like the knee of a Zener diode or something like that. This is the VF of a regular 1N4148. It's around 700 millivolts, regular silicon diode. And look what happens when you put it at 77 Kelvin. So not only the VF almost doubles to over 1 volt, but the equivalent series resistance of the diode, so the slope gets much, much shallower. which is very interesting. So it becomes a much worse diode at very cold temperatures. Okay, this is the breakdown voltage of a Zener in reverse at room temperature. It's around 150 volts, something like that for 1 milliamp. And at 77 Kelvin, it does a very, very weird thing. So again, it drops, the voltage drops, and it has the same knee characteristic here like that. And yeah, it's very, very interesting. I never expected it to be like that. And here we have a Zener voltage. This is a 5.6 volt Zener, and it's pretty reasonable actually. It's not bad. You can see that the slope is very vertical, so it's a pretty good diode. The current through it doesn't influence the voltage that much. And at 77 Kelvin, not only it's not even what it's used to be, like a 5.6 volt Zener, it's 5.3 volts. Its slope has gotten much, much worse. So yeah, I don't even know what to tell you about these things. Semiconductor physics is weird, and so as not to speak out of my ass again, I would like to call it a day. I wanted to do more things about transistors, but I'm running out of liquid nitrogen. Apparently this thermos flask isn't very insulating after all by the amount of snow that's built up on it. But let's try a couple of more things. I'm gonna take a short break from breathing in nitrogen, and then I'm gonna come back and try and give you a couple more experiments. Maybe stick a capacitor in liquid nitrogen and see what happens. And yeah, okay, I'll be right back. Alright, so apologies for the terrible viewing angle. I have one of these plain film capacitors, and I'm just going to dip it into the LN2. And you can see the capacitance is dropping quite significantly. 42 nanofarads, and it's leveling off around there. So this isn't a very susceptible capacitor, because like from room temperature to 70 Kelvin, dropping like 10% or something like that of its capacitance, that's pretty good in my book. Let's try an electrolytic. I'll be right back. I need to find a very small electrolytic capacitor. Actually, first of all, I found the 100 nanofarad, the ceramic disc capacitor, like the cheapest of the cheap ones. And you can see that if you dip it in liquid nitrogen, it's not really a capacitor anymore. So if I warm it up, it's a very, very good temperature sensor. I would go for calling it that. So 4 nanofarads, so it's left with around, let's say, 5% of its initial capacitance, which is crazy if you think about it. And there seems to be some sort of hysteresis in it as well. Not really. Anyway, that's really interesting. Alright, so let me try and do one of those conclusion things again. Cold temperatures are very interesting, especially due to the fact that they screw around with the very fabric of the things around us. Everything from charge carrier mobility and stuff like that, to basically how the molecules interact with each other at cold temperatures is vastly different to what happens at room temperature. So until I get a like a Stirling cryocooler to have a regular on-tap supply of liquid nitrogen, this is really all that I can do for a while, considering that getting this was kind of difficult, and storing it is kind of not that safe. And by the way, don't ever try and do what I did today. Liquid nitrogen is very dangerous. Um, if you're not careful, it can freeze your arm off, fingers off instantly, and getting insta-frozen from liquid nitrogen isn't very pleasant. And you can also asphyxiate basically due to the fact that it tends to boil off into large amounts of vapor, basically into large amounts of gas, and it can displace the oxygen in the room. So always make sure that you work in a very well ventilated place. With that said, it's very, very cool and interesting, and it can have a lot of applications in every field. Like, you can do a lot of research using liquid nitrogen, and it's a very important. It's not a chemical. Well, everything is a chemical, but it's not a chemical per se in the chemistry reagent style of talking. But it's a very important technological fluid. Let's call it that. So, with that said, I hope you found it very interesting as I found it. I was really ecstatic about trying the things that I tried today, and showing them to you. And I hope to see you next video. I have no idea what it's going to be about. If you have suggestions, leave them in the comments, and I'll happily select something if I can do. You'll see it. Okay, thanks for watching. See you next time. Bye bye.